With estimating and simplifying square roots, I mean, it's always good to understand what a square root is. Like, if you can understand what it is, then hopefully it will help you to find it, especially when we look at perfect squares, which is what we're going to start with. But a square root is just, it's like a question that asks, if I give you the area of a square, can you tell me the side length? Now, one thing we need to remember about squares is that, let's see if I can draw this. Okay. Yeah, something like this, okay? And we should know this about squares is that the side lengths of squares are all the same, right? Now for squares, since they are the same, instead of using length and width, we say side and side. So it's S and S. So if I said, well, let's find the area of a square, you'd say the area of a square is the side length to the power of 2. And I know some of you guys wanted me to write S times S, and my students that I teach during the day think that's hilarious. But in any case, all right. Sorry to disappoint you on that, but yeah, that's I don't know. I like this anyways. Area equals side length to the power of 2. So side length times side length. Okay. Now again, the main thing we need to remember on this is that the side length is the same, instead of it being like a regular rectangle where it's length times width. So this symbol as well up here at the top, this one right here, that's our square root symbol, and it is on your calculator. You guys can see on my calculator, just to the left of 7, you got the x to the power of 2 button, and then right above that in green is that square root button. So when I need to access it on my calculator, I just push second and then x squared. For those that have Casios, it by itself should be its own button. So you should see a button that just shows this square root symbol. Now in this example, it says this one right here, it's the square root of 100. Again, it's the same thing as asking, what is the side length of a square if the area of that square is 100? So in this square, would say, well, let's say that this area is 100. Well, what would the side lengths be? Well, it's got to be some number multiplied by itself, right? Because it's side length times side length. Well, in that case, you'd know that it's 10 times 10, right? Now this would be a perfect square because it's a whole value, 10, no decimals. It's not really a fraction, and it's being multiplied by itself. 10 times 10 is 100. Now, something else about area, and I think we've talked about this before, is area, and it shouldn't be asking for area, but just in case it does, remember that it's always in some kind of square units, all right? So if you wanted to write it as units squared, you could, but if you wanted to write it out as square units, that's fine as well. When we look at square roots, we're finding the length of one of the sides of a square, not necessarily the area. So if you guys can just memorize these first 12 perfect squares, all right, then you'll be in really good shape to do all the stuff we need to do in this part of the module. One other thing I want you guys to notice is, right, so power of 2 just means that it's some number multiplied by itself. So like 1 to the power of 2, it's 1 times 1, which is 1. Anything times 1 is itself, even if it's 1. So 2 to the power of 2 would be 2 times 2. And you can write it as 2 to the power of 2. It's 4. And then you can go down the line. But let's just skip over to maybe 8 times 8, right? We know that's 64. And 11 times 11 is 121. Well, if we just look at this in terms of the powers, though, like these powers of 2, if we compare them to this column right here, hopefully you guys notice that it's taking these values in this column and just square rooting them right here, right? And then when you square root those values, you get the original value that we started, or the base value that we started from, whatever it was, to the power of 2. And this is because it is asking what the side length of a square is if the area of the squares are these numbers. So again, the square root of 81 right here, it's asking, well, what's the side length of a square that has an area of 81? It's 9, because 9 times 9 is 81. So again, if you guys can remember these values, these 12 values, which is just the first 12 perfect squares, then this goes a lot faster. Now, if you have trouble memorizing that stuff, it's okay. Of course, we'll still be using the calculator, but you know, if you were to print this out, perhaps, and then post it somewhere that you see often, then I think you'll find these are memorized in no time. The square root of 81. Again, this is just saying if we have a square with the area of 81, what is its side length? Well, that was part of that list that we just saw. Square root of 81. Well, that would be 9 times 9. So it's just 9, okay? Now, is there another number that multiplies by itself to get 81? There is, but we're just looking at the principal square roots when we look at these values, okay? So you'll look at that in a little bit more detail in 980, but for now, we're just looking at this 9 right here. All right, negative square root of 196. Again, this is asking if you had a square with an area of 196, what is its side length? Well, that wasn't on the list, and that's okay, because if it's not on the list, then I would go to the calculator, which we have set up already. Square root 196, which is 14. Now, this is 14, but just almost like the way the absolute values work, is this one has a negative out in front of the square root. So it's really saying it's the negative of whatever value we get, which in this case is 14. So I'm going to make the 14 negative. And that is complete. Now this may feel like it's going pretty easy right now, which I hope it is, because all of these are going to be perfect squares. We're gonna look at a method to simplify these if it's not a perfect square. All right, here's a decimal value, but one of the value that I want you guys to look at in this one is this 25 business right here, okay? I'm not really worried about the zeros right now, but I know if this was just the square root of 25, then my answer would be 5, right? That's an equals. So even though this is a decimal, it's going to be related to 5 somehow. And again, just to do this one, I would just go to the calculator. Square root of 0.0025. And this will tell me what it is. And again, we see the 5 right there. It's just 0.05. So again, recognizing the 25, which is one of our perfect squares, in this decimal is pretty crucial. I mean, we still use the calculator, but if you can recognize that, eventually you'll notice a pattern with these zeros out here in the front. Now, we're not concerned about that right now. We just want you guys to be able to find these, and if you need to use your calculator, that's okay too. All right, the square root of negative 36. So 36, if this was just the square root of 36, like this, then we could say, well, this is 6, right? So something with this square root of negative 36, it's probably related to 6, right? Now, if we go to the calculator, though, square root of negative 36, and there is a difference between what we saw before, which had the negative in front of the square root. So if I saw the negative square root of 36, I know that's negative 6. But what about the square root of negative 36? I push enter, and it says it's a domain error in the calculator. What does that mean? Well, it means that if we were to look at a square, again, we would need some value multiplied by itself to be negative 36. And in this case, we know that it's related to 6. 6 times 6 is okay. It's just that it becomes this positive 36 right here. Well, the only other option we have is to make this negative. But if one of them's negative, the other one has to be negative as well, because it's the same thing multiplied by itself. And negative 6 times negative 6 is also positive 36. What this means is that, for now, there is no real value that would give us this answer. Okay, so in this case, we're going to say that it's not real. On the homework, I believe it comes out as one of those DNE, does not exist problems. But you'll find in 980, no, I think it's 1010, that you will be able to actually work with these negative square roots later on. But for now, we just say, look, it's not really in the domain that we're looking at, which is all the real numbers. And yeah, if we say it's not real, that means that there is such a thing as a actual not real number. You got real numbers and not real numbers. And yes, math people, once they ran out of all the real numbers, like calculating with them, they're like, dude, I'm running out of math to do. I've got to do more math. And that's when they ran into these imaginary numbers. But we're not concerned about that right now. That's a really good question. Let's address this one, and in fact, let's adjust it just a tiny bit and just say that it was the square root of 196. All right. So new example. Square root of 196. Okay. So let's say that we're like, look, this one isn't in the perfect square list, and you could use the same method with the perfect square list. Okay. It's just the method still applies, and we're going to get into more detail in this one here in a few minutes. But for the square root of 196, would say, look, I can make factor pairs, right, or a factor tree, which is just prime factorization of 196. Well, 196, I can see it's divisible by 2. I'm not too familiar with 196. So if it was 2, I'd divide 196 by 2. And what would I get? I'd get 90, 93, 98. Oh, sorry. It's supposed to be my eraser. 98. Well, I see 98 and 2 is prime, so I circle that one. 98 is 2. It's divisible by 2. Well, 2 times what? 2 times 49. Well, 49, it's not divisible by 2. It's not divisible by 3 or 5. So the next one I would think about is 7. 49 is divisible by 7. It's 7 times 7. So the prime factorization of 196 is 2 times 2 times 7 times 7. And what I want to notice on this is I need pairs of factors that are the same, such as 2. Okay, so one of my factor pairs that are identical is 2. The other one is 7. What we do with those is we multiply those together, because these are considered independently perfect squares, right? 2 times 2 gives us a perfect square of 4, and then 7 times 7 gives us a perfect square of 49. So this is kind of like looking at the area of 2 different squares, and then we've just found the 2 side lengths which make those 2 perfect squares. So just multiply them because they came from the same number, and we get 14 again. And it's a good question, because I mean this shows that again it's the definition of what a square root is. Well, it's the area of a square. What is the side length? Well, we found 2 that work in this case. Just don't forget to multiply those in the end. But yeah, the reason why I showed this method specifically at this point is not only because you've asked, but also because this is the most common method that's used amongst students. I mean, sometimes they use the other method. It's again, it's really up to you guys. But yeah, this is a good place to show that. Now, the square roots of fractions, we shouldn't see a lot of fractions that have, I don't know, weird stuff in it, okay? So in this case, when we see the square root of a over b like this, we should only see perfect squares that I remember in the homework. Now, if you do, and for the most part, we hate fractions. Fractions have ruined many lives, which we are very sad about. I think most mathematicians are sad about it. But in any case, all you're going to do is you're going to take the numerator and square root it, and you're going to take the denominator and square root it separately, okay? So when we see an example like this one, all I'm going to do is I'm going to take the square root of the numerator and the square root of the denominator. So it's the square root of the numerator, which is 1, square root of the denominator, which is 144, and then you just find those separately, okay? Well, the square root of 1 is 1. The square root of 144 is 12. Now, don't forget, this one did have a negative out here in the front, so it also makes the fraction negative, and the final answer is also negative. So, the final answer on this one, negative 1 over 12. All right, so splitting up the square roots, the idea is to manipulate the square root into separate values. So we're just looking at factors, and in this case, it's showing a factor pair of some number, right? Which we saw with 196. So if we looked at this 196 example, what we really did is we split it up into two factor pairs, which was 4 and 49. Well, those are both perfect squares, and it still would have been the square root of those. The square root of 4 is 2, the square root of 49 is 7. You multiply those together, bam, you get 14, which was the answer to that. But, and again, we could have written this up here like this. It could have been the square root of 4 times 49, which is what allows us to break it up into two separate square roots that are being multiplied together, which is what this rule is showing right here, okay? So you can look, and again, this is all about manipulating the numbers to be what we want them to be, right? I'm not familiar with 196 again, but if I split it up into these two values, I am familiar with those, or these. These, again, mean the same thing, which then allowed me to find those values and work with them instead. So that was one of our methods, is just to find the greatest perfect square factor, the greatest perfect square as a factor, you could say. So you just find factor pairs of the value, you find the factor pair that is the greatest perfect square, and then you take the square root of it, okay? Now, if the other one's not a perfect square, I mean, in the square root of 196, both of them were perfect squares, but if one of them is not, you just keep it in the square root. So if it's a non-perfect square, you keep it in the square root. If it is a perfect square, then find its actual square root. But the other method is prime factorization, and again, this is the most common. There is a method C. We've talked about it, but let's look at these two first. So let's use both methods on this one, okay? So the square root of 12. Now, let's try the first method. What do we say? It's method A. So I'm going to find the greatest perfect square factor of 12. So 12, it's got some factor pairs. I mean, 1 and 12, sure, that's fine. But the square root of 1 would be considered a perfect square. But we don't really consider that value because it's just the identity property with 12, okay, of multiplication. So the next one I would say is, well, 2 and 6. Well, 2 and 6, neither of these are perfect squares, so that doesn't really help us. The next set of, or pair of factors for 12 would be 3 and 4. Now again, this is kind of the importance of memorizing, or the convenience of memorizing the perfect squares, the first 12 perfect squares. Is right here, I notice a 4, okay? So, 4 is a perfect square, which means I could take the square root of 12 and break it up into, I'm actually going to switch those, 4 times 3. Again, I haven't changed the value. 4 times 3 is 12. So I'm just manipulating this as much as I need. Well, now that I have a square root of some number times some number, I can break it up into 2 square roots that are being multiplied, like this. Well, the square root of 4 is 2. And the square root of 3, like we said in that method A, it's not a perfect square. So I just keep it in the square root, and that completes that simplification of this square root of 12. Now that was method A. So the square root of 3, no change, right? Now again, that's because in the method it's if the non-perfect squares, which 3 is not a perfect square. We just keep that in its square root. The square root of 4, however, is a perfect square, and I know that the square root of 4 is this 2 right here. Now these were being multiplied, so I keep these being multiplied. I did not show the multiplication. You don't have to. Like I said, math people are pretty lazy, which is why they don't show this multiplication right here. If you want to, that's fine. It still means the same thing, but the orange 2 here, it comes from this square root of 4. Let me add this step here. Okay, so let's get rid of this stuff here. The next method is the method that most students choose to use. So I mean, whether you prefer it or not is really up to you guys. Okay, so I'm not here to say one of these methods is better than the other. I have a method that I prefer, which we'll show you guys here in a minute. But to expand on this one, right? The square root of 4, it could also be broken up into 2 times 2. And then again, you'd have it multiplied by the square root of 3. Now, the reason I'm showing the square root of 2 times 2 is because 2 times 2 makes it a perfect square. We're looking for some number multiplied by itself within the square root, right? Because this is saying, let's go back to the definition of the square root is, if I give you this area 4 of a square, can you tell me the side length? Well, the side length has to be 2, because it would be 2 times 2 is 4. So the side length of a square that has an area of 4 would be 2. Well, can you tell me what number multiplied by itself would be 3? And the answer to that right now hopefully is no, because it's a pretty ugly decimal. And again, we know that 2 times 2 would give us that area of 4. So it's one of the side lengths is that orange 2 right there. And then we get this answer right here. Now, that adds an extra step. I don't know if that fully clarifies what you're asking, but it does kind of show maybe in more detail where that 2 comes from. The third method, and I'll still talk about the second method. The third method is my preferred method, which is to use a calculator like you're doing here. So for me, when I type these in, right, we're looking at the square root. Well, let me clear that screen. Square root of 12, and again, we've shown the using the calculator with the perfect squares. It works with non-perfect squares as well, as long as we're using this TI-30XS or that Casio FX300, whatever it was. Okay, the Casios will also simplify these square roots for us. Okay, now, like you said, if you're looking at moving or working backwards, if you looked at this 2 square root of 3, I mean, you could work backwards like this. Well, I don't want the side length of the square, I want the area. So if the side length is 2, then the area would be, again, it's a square, so 2 times 2, which is 4. But now it's the square root of 4 times that square root of 3. Well, I'll just combine them. 4 times 3 square root. Square root of 4 times 3 is 12. So this works down towards the simplified square root. This one works, I would say, in a backwards way. Again, I don't know if that really helps, but in any case, the calculator did give us that answer. Square root of 12. This would be method C, I guess. This one was method A. So method C is the calculator. The calculator told us it was already the square root, 2 times the square root of 3. Now we do have method B, though. Square root of 12. And this is just the factor tree business that we did with the square root of 196. So 12, I'm just looking for any factor pairs of 12. I'm not really looking for a perfect square. So I could say, well, it's 2 times 6. Well, 2 is prime. So it's a prime factor tree. And then 6 would split up into 2 and 3, both of which are prime. So the square root of 12 is really the square root of 2 times 2 times 3. And again, this is all about noticing a pair of values in the square root that are identical, like 2. Well, that's the square root of 2 times 2 times the square root of 3. And the square root of 2 times 2 is 2. So it's 2 times the square root of 3. And then it shows that we get the same answer. And, you know, I'm glad you bring that up because, I know I've seen this maybe somewhere in secondary education, which it is taught, of course. It's just one of the things we find with this, and I'm sure you guys have found it too, is we don't deal with square roots very often, right? Like, how often you guys in life are given the area of a square and they're like, hey, find the side length of the square. So we don't deal with these too often in life, which is why these may seem kind of familiar, but maybe you've forgotten about them, and this is a good review. But again, as you guys go through the homework and as we see these examples, hopefully a lot of that stuff that was taught to you back in the day will kind of come back to you guys. So we've seen all 3 examples. You guys choose which method you like the best and see if you can simplify the square root of 150, all right? We'll give you guys 1 minute to do that. 1 minute, go. All right, guys, hopefully that was enough time. But so we've got 3 methods that we can use on this. Which method you guys want me to use? So let's go back then to, I'll start with method A, then we'll go over method B. So method A, starting out, square root of 150. Now again, I would be looking at any perfect squares of 150. Now I always start with my factor pairs. It's not a tree, sorry. I would look at factor pairs starting with, I guess, my lowest one that I know. And I see right here that 150 is even, so it's at least divisible by 2, right? It'd be 2 and 75. Well, 75 is not a perfect square, and neither is 2. So I would move on to my next set of, or pair of factors of 150. So that would be, I know 150 is divisible by 3 because 1 plus 5 plus 0 is 6. And 6 is divisible by 3. So it is divisible by 3. 150 divided by 3, bam, 50. All right, well, neither of those are perfect squares either. So I move on to my next pair of factors for 150. So it's not divisible by 4, though. It appears that it is divisible by 5. Let's try that one. Well, 5 times, what? 5 times 30, I guess. That would be 150. But again, this is a pair of factors of 150 that are not perfect squares. So we need to go even further. Is 150 divisible by 6? It is. It is divisible by 6. Now you may be wondering how I know it's divisible by 6. It's because we have 2 and 3 as factors of 150 here. So I know it's divisible by 6. Well, that'd be 6 times, what would that be? Let me see, 25? Oh, there we go. 6 and 25. Now, this is as far as I need to go in terms of making factor pairs for 150. And you probably notice that there are more factor pairs of 150, but I moved through the list starting on my left with the smallest value. So I know there's 1 in 150. Again, I'm not concerned about 1. But then we got 2, 3, 5, and 6. So you can see how I'm kind of moving up with the lowest factor. And then I found 25. Multiplied by 6 is 150. I don't need to go any further because 25 would be considered my biggest perfect square factor of 150. So 6 is the non-perfect square in this. Okay, so again, I would be looking at these both separately as square roots. Well, square root of 6, again, that's my non-perfect square, so it just stays in my square root. Square root of 25 is 5. Now, it's not traditional in mathematics to write the square root in front of the perfect square, which is in the orange there, the 5. And the reason that is because sometimes it's hard to interpret if this is the square root of 65 or if it's the square root of 6 times 5. So, in order to stop that confusion, we just write the 5 in front of the square root like this. Okay, so this would be considered more proper in traditional mathematics. 5 times the square root of 6. So that was method A, though. And as promised, we'll look at method B. So method B, we got factor tree. All right, well, still looking at the square root of 150. So we'll write that out, 150. And again, the thing with the factor trees for prime factorization is we're looking for pairs of values that multiply together, which would give us a perfect square. So 150, it splits up. Maybe some of you guys noticed that it was 10 and 15. Okay, because it ends in 0. So it's divisible by 10. So I'm just using a different pair of factors of 150, not only to show that there's more factor pairs than what we listed there on the left, but because it doesn't matter with prime factorization as well. So 10 would split up into, let's say, 2 and 5, both of which are prime. And then 15 splits up into 5 and 3, both of which are prime. So in my list for the square root of 150, I would have 2 times 5 times 5 times 3, which is the square root, okay? Now, again, for square roots, we're looking for pairs of values that are the same, which is this 5's. So the square root of 5 times 5 is just 5. All right, well, then we would have the square root of 2 times 3 as well, because, again, those are not, we didn't find any pairs to work with the 2 and 3, so that ends up being just the square root of 2 times 3, which is 6. So we end up with 5 times the square root of 6. Same answer, different method, although they are kind of similar. Now, in this example, we only found one pair. We saw with the square root of 196 that it is possible to have 2 separate pairs that match. So if that happens, it is possible to have maybe, like in this case we had 5. Maybe it could be like 5 times 6 or something like that, okay? Or 5 times 7 or 9 or 11. It doesn't matter. But you can have more multiplication out here in front, in which case you would multiply those numbers and get some other value here in front of the square root. Now, I didn't say we were going to go over method C, but I do like it enough that I want to, because it's my favorite method. Square root of 150. So I just type it into my calculator. Bam, it pulls out 5 times the square root of 6. Square root of 150 equals 5 times the square root of 6. So, for me, that's a good way to confirm it, but it's also a good method unto itself. Now, I'll tell you guys this as well. I just kind of listed these numbers randomly. You guys may find that a lot of, I would say textbooks even, they list these kind of in order on purpose. So the way that I've done it is it's very randomized, right? Like we just said, the square root of 10, or the factors of 10 are 2 and 5. The factors of 15 are 5 and 3. But in this square root right here, generally speaking, they usually put the pairs of values that match in front. So 5 times 5 times 2 times 3, which allows them to break it up into 5 times 5 square root times the square root of 2 times 3, which I don't know if it makes more sense for you guys or not, but it's just one of the things they do to make it easier to organize that stuff. So if you prefer to do it this way, to order them like this, that's okay. This is just the commutative property of multiplication, which still applies inside the square root like that. Well, here's a number with 7 times the square root of 72, right? Now, I'm not concerned about that 7 until I find perfect square roots of 72, right? So, again, let's look at both methods on this one. We got method A, which we'll start with. Now, it is 7 times the square root of 72, but I'm not concerned about the 7 yet, okay? I'm only looking at 72, and I want factor pairs of 72 as well. So, a factor pair of 72, again, I'm not concerned about 1. It's going to be a factor of any number. But it's even at least, so I know it's divisible by 2. 2 and what? Bam, 36. Well, again, I start with my lowest one on the left there, 2. And I've already got a perfect square, 36. So I don't need to go any further. This would be the square root. Again, I'm going to change it up almost for convenience and order. And this allows me to break that up into 36 times the square root of 2. Now, 36 is a perfect square. It's 6, right? 2 is not a perfect square, so I keep it as a square root. But this is where I need to reconsider the 7. It's being multiplied by the square root of 72. So where I found that the square root of 36 is that red 6, I need to multiply it by the 7. So 7 times 6 is 42. And then I just keep the square root of 2. So this would be the answer for the simplified form of 7 times the square root of 72. Method B is going to work the same way, but again, I would, I don't know, still be looking at that square root of 72 first. Okay, so again, I'm not really concerned about the 7. 72, let's look at some prime factors of 72. Again, I would be thinking 2 and 36. Now, some of you guys notice the 36 there in green, which is a perfect square. And if you notice that, you could just take the square root of it right now. But let's say we didn't. 36 is also divisible by 2. 2 times, let's see, 18. So 18 splits up, let's say, into 3 and 6. And then 6 breaks up into 3 and 2. All right, well, that's a good factor tree. That means that the square root of 72 is the same as the square root of 2 times 2 times 3 times 3 times 2. So, just like we did before, I'm just looking for pairs of values that match, like the 2's and these 3's. Now, you may be wondering, well, what about this 2 right here? Well, I already found a set or pair of 2's that matched. There is no other 2 to match with this one, so it's just going to stay in that square root, right? Well, this is the square root of 2 times 2, which is just one single value 2. And same with the pairs of 3, since it's a square root, it just comes out as the side length of 3. Well, 2 times 3 is 6. So we got 6 out of that. 6 times the square root of 2. Well, that's different than the answer that we have over there. That's because I haven't factored in the 7. 7 times 6, still 42. And then the square root of 2 is still the square root of 2. So again, it's the same answer, different method, and it works. But like I said before, I really like method C, which is just to type this into the calculator, which we can do. So I just type in 7 second x squared. That gives me the square root. Then I type in 72. And again, the nice thing about these calculators is it does simplify it for me, which we see right there, 42 times the square root of 2, which confirms that we did it correctly. Now the calculator method is nice and it's very convenient. There are some problems where you will have to use the calculator unless somehow you know and are familiar with non-perfect squares, which is very, very rare. Okay, so just so we look at this, you'll need to find and access the square root button. On a computer, it's gonna maybe look something like this one right here. Okay, this one. On the TI-30XS, again, it's right to the left of 7. On older TIs, because I find a lot of students have some older TIs like this, it's going to look like this one right here. That's a pretty picture. And I think it is also to the left of 7 or somewhere in that area. For the Casio FXs, it's going to be its own button like this one. Okay, so you don't have to access it through the shift key. It's just its own button, which makes that very convenient, okay? So this is where we have to have a calculator, again, unless you're just, if you're familiar with your square roots up to like 972, man, that's more power to you, because I'm not good with that kind of thing. So I'm going to go to the calculator on this one, square root of 972, right? So square root 972 equals, now this one simplified it for us. So that would be considered the exact answer for this one. Okay, so there's two answers: simplify exactly and estimate to the nearest thousandth. This is exact. 18 times the square root of 3. So that's one of our answers, and that looks pretty good. The other answer is the decimal value to the nearest thousandth. Now on the TI-30XS, I'm going to push this arrow key right above enter. And I push that, and it gives me the decimal. For those of you using a Casio, you've got to push the SD button. It looks something like this one. S, and then it's got like a double arrow D thing. Yeah. A button like this. It's right above the delete key, for mine anyways. So if you push that button on the Casio, it'll give you the decimal as well. And again, this one's showing I'll write the whole value right now. 31.17691 454. I think I copied that down right. Now again, we don't need this full decimal. And in fact, this is not the full decimal anyways. So if we ever find a square root of a non-perfect square, it's what we call an irrational number, which just means that this decimal, it's going to go on forever and ever and ever, and never repeat or terminate. Maybe you wanted to know that, maybe you didn't. In any case, let's go and round this, okay? So it says to round the nearest thousandth. So let's identify the thousandths place value: tenths, hundredths, thousandths. So I'm looking at the 6. I go to its right at the 9, and I say, well, 9 is 5 or higher, so I add 1 to my the place value that I'm rounding, and that gives me a 7 right there. So this ends up being 31.177, rounded to the nearest thousandth, and of course we would have put zeros on the rest of these numbers. So this would be the estimation to the nearest thousandth. All right, same thing on this one. 4 times the square root of 128. So again, for my exact answer, I'm just going to type that into the calculator. 4 times the square root of 128. You guys notice on my calculator, I did not type the multiply. The calculator already knows that without typing the multiplication in, that it is actually multiplication. So I just push enter, and it gives me 32 times the square root of 2. So that's my exact answer. That's not the best 3 I've ever written. And then again, for my decimal, I'm going to push the arrow key right above the enter button, which changes that into a decimal. Now this is 45.2 2548. And yeah, there's more decimals to that, but this is all I need to round to the nearest thousandth. So my thousandth place value is the 4. I look to the right, the 8. Well, that's 5 or higher, so I'm going to add 1 to the 4, which then makes it a 5 in the thousandth place value. So I've got 45.255. And that would be my estimation to the nearest thousandth.